you have a specific question, especially if it's a practice exam question, make sure to tell us the page and the, just the page number and the number of the question. Okay, just by raising hands, who's first? Yes. Oh, yeah, your kind of electrons S will always have one orbital, so it'll have 2 electrons. P has 3 orbitals, P, X, Y, and Z, so 2 each, so that's 6. D will have 5, so a total of 10 electrons, and F will have 7, for a total of 14 electrons. 2 per individual orbital. Yes, that's right. Yes? What's the shading? Shading means they're out of phase with each other. And so that essentially means, just like if you vaguely, we're going to revisit this when we do the constructive and destructive interference. But if, like, see how if this starts here and this one starts here, they're out of sync with each other, the wave functions. And that happens, this is a 2D example, where it's flat. That can happen in 3 dimensions also, where they're out of sync with each other, just when you calculate out the wave function. So for a p orbital, the top and bottom are out of phase. Yeah. And so that could cause destructive interference, which we'll see in chapter 10. Yeah. If you want to know more, ask me later. Yeah, that's getting more into chapter 10. Okay, who's next? Yes?
Would the sulfur anions still be smaller than strontium? You said it was just
yeah, let me write that out first. So let's say, first if we had sulfur and strontium, we did this earlier, strontium would be larger. It's more to the left and down. Now let's say we had a strontium 2 minus, or sulfur 2 minus versus strontium. I usually wouldn't give you something like so way apart on the periodic table, but if you had to guess, I'd usually go with the anion as being the larger one. Yeah, even if they're kind of far apart, though I usually wouldn't give something that splits the periodic table in half. Give something a little more reasonable.
Okay.
Yeah. Okay, who's next? Yes?
Do you happen to know how to calculate R, the 4 radius?
Oh, can I see this one? Yeah, no, you wouldn't need to know that. So, what's being asked is, would you be able to calculate R as far, if there's a node? So if there's a node calculating R in terms of A naught, no, you wouldn't need to do that on our exam. There is a place on the homework that you would have to do that at one point. Yeah, we had that on past exams, and that was removed from the curriculum. Okay, who's next? Yes? Yeah.
The constant, when you put H, that was like constant.
And all the questions about wavelength? Yes, that's right. For a wavelength, if you ever see H, that's Planck's constant in chapter 7. The only place that we use it as a different variable is chapter 6. What's H? Anybody? Height. In a specific formula of pressure, density, gravity, height. So this is the only place where it's not Planck's constant, as far as I can remember. Yeah. Okay. It should be obvious from the context. This would be a pressure under a liquid kind of question versus anything about a gas or a quantum theory. That always be Planck's constant. Okay. Who's next? Yes.
Can you do number 25 on page 106 in the practice?
Okay. Practice exam reader, page 106. Number 25. Okay. So let me just show this to you so people can see it, first of all. All right. We have aluminum reacting with HCl. There's H2 is liberated and collected over water. This is a Dalton's over water. I see the keywords. At 25, we see the pressure is given. The vapor pressure water is such and such. So I don't even have to look this up. It tells me what the vapor pressure water is. And And let's see. They want to know a couple things on the next page. So let's try and solve this, see what's being asked for, and this will be a pretty typical Dalton's over water sort of question. First, let's get the reaction down. It's aluminum plus HCl. So this is what kind of reaction? Anybody? This would be a single replacement reaction. We need a 2 and a 6 and a 2 and a 3. Okay, there's our reaction. What's the partial pressure of H2 in the mixture collected? So this is the first equation. If you were here earlier, let's write that down. P total is going to equal the partial pressure of the gas, which is H2 in this case, plus the partial pressure of water, or the vapor pressure of water. Okay? Total pressure is given in the question. That was 744 millimeters of mercury. So this is given, 744 millimeters of mercury. The partial pressure of H2, that's what we want to know. The partial pressure of water, if it was not given, you'd look in the table, but that was given, and it's 23.8 millimeters of mercury. Okay? So you just solve by subtraction for the partial pressure of H2. Since I have the answer right here, I will just tell it to you. It turns out to be 720. Okay, that's the first part of the question, was the partial pressure of H2. Now, the second question says, how many moles of H2 gas is formed? Okay, now I'm talking about moles. I've got the pressure, I've got the temperature. This is an ideal gas law problem now. So let's change colors here. I'm going to work with the ideal gas law, PV equals nRT. Temperature is given, R is a constant, moles is what I want to know. I've got the volume, I believe. Yes. I believe I have the volume. Let's see. Water. Oh, maybe I don't. Let me see. Oh, it's even easier. Oh, yes. It is even easier than this. This is so awesome. They tell me 1.65 grams of aluminum. If I know the grams of aluminum and I have the equation up at the top, all I have to do is stoichiometry. So the second part's actually pretty easy. So what would I do? I would say, well, let's change this to moles. 26.98 grams per mole from the periodic table. So that's moles of aluminum specifically. And then there's 3 moles of H2 for every 2 moles of aluminum. And let's see, they wanted to know the moles of H2 gas formed. That'd be this number. And that turns out to be, let me see if I can find it here, 0.0917 moles. Moles of H2. So that'd be the second part. That's your stoichiometry. That's no gas law stuff whatsoever. Part C, now what's the volume of gaseous mixture collected? Here is where I do have to use ideal gas law. So let's go back to this again. Bring it back down here. PV equals nRT. Temperature is given. R is given. Moles I just found. Volume is what I want to know. And pressure was from part A. So let's plug this in so you can see what it would look like. Volume is nRT over P. N, I just found 0.0917 moles. That's from the previous part written right here. R is a constant, 0.08206. Temperature, let's see what the temperature was in the question. 25 degrees C. 25, which you got 273 to change it to Kelvin. And the pressure. Pressure was from part A, and that's 720 millimeters of mercury. However, those units aren't helpful in ideal gas law. I need to change to atmospheres. That conversion is given on the exam. 1 atmosphere per every 760 millimeters of mercury. And that equals 2.37 liters. Is that okay? Okay. So the middle one was just to add some stoichiometry into the question. The typical parts are A and C for a Dalton's law question. All right, who's next? Yes?
What kind of questions would would you ask regarding wave functions?
What kind of questions would I ask regarding the wave function? Well, what possible questions are there? What's the value of a wave function at a node? Anybody? 0. That's a question. I could have you write out a wave function, in which case, let me flip to, well, let me show you this. I have had people see this equation. This will be given on the back of the exam. I've had people literally copy something out of here. So what's the 1s wave function? You'd put this times this. So literally, see if you can copy, write that down. And then it would just be conceptually regarding the wave function. So this wave function has how many nodes? But then you're getting away from the wave function itself. So that's about it. Yeah, that I can think of right now at least. Yes? Okay. Do I need to come over there? Or? I don't know. What would be easiest? Let's see. Well, I get a free computer out of this. You all, are you watching this example here? Okay. This is also, so see the keywords collected over water? Same sort of question as before. Sweet. I like the cover too. Okay. Although I don't know about the pink, but I can go with that. Okay. So her question is from, looks like Mastering Chemistry. We've got O2 gas collected over water at 24 degrees C, and the volume is 1.17. So here the volume is given. In the previous question it was not. In a subsequent experiment determined the mass of O2 present was 1.45 grams. Okay? What must have been the barometric pressure when the gas was collected? Oh, it also gives us the vapor pressure of water, 22.44. So what do they want to know? They want to know barometric pressure, or P atmosphere. Okay. Well, this is a similar sort of question as what we saw earlier. So P atmosphere, that's P total, same thing, is equal to the vapor pressure of the water plus the vapor pressure of the gas, in this case O2. So let's just get our pen out. This is that one right there. Okay, so we know the partial pressure of water. How about O2? We can calculate that. We'll use the ideal gas law because I have temperature, I have volume, I think I have everything I need to use the ideal gas law. Let's try it out. So let's try this. PO2 would be NO2 RT over V. The volume is 1.17 liters. That's the easy one. Moles. How would I find moles? Anybody? Yeah, I've got the mass right here. 1.45 grams, and the molar mass of O2 is 32 grams per mole. R is 0.08206, and the temperature is 24 Kelvin or 296, or 24 Celsius, which would be 296 Kelvin. That should be it. This number would go here. Now, what would be one problem I'd run into? Yeah, a unit issue. This would be in atmospheres, this is in torr, so you need to switch those around. But I assume, would you be able to figure that out? I'd switch, depending on what they ask for. They want the answer, it looks like in, oh, I don't know what they want the answer in. But whatever units they want the answer in, that's how you'd want to report it. Is that okay? Don't worry, I'll give this back to you, though. Cool. Okay, who's next? Yes, oh.
Why don't we have to change it to kilograms?
In this question, why is it not changed in kilograms? This is not a SI unit question, or the ideal gas law is not an SI unit equation, I should say. And because 1.45 is in grams, I'm just going to use grams to cancel the units. And so there's no kilograms in the question. I don't need to convert to kilograms. Okay, cool. Who's next? Yes?
For the uncertainty principle,
Yeah.
let's say instead of accuracy, you give uncertainty. like 6% uncertainty and velocity. Wouldn't that be like 0.94 if you multiply it in the
Oh, I see what you're saying. It's talking about if you're given in a question from the uncertainty principle, 6% uncertainty, really what it would say is 6% accuracy. And so that's why we're using, yeah. So it would say 6% accuracy, so you're going to use 0.06. You don't need to subtract from 100. Yeah. And that's pretty standard. It would be very unusual to go the other way. And typically the percentage you're given would be less than, say, 10%, is what you're expecting. Yes?
Wait, so you're using the percent accuracy?
Yeah, which is what's...
So
you're using,
if they give you uncertainty, then that is not 1 minus uncertainty?
if they give you the percent uncertainty, I don't know, I'd go crazy. Because that would just be, it would be really unusual to have that happen. In a typical problem, we give you the percent accuracy. And you just use that number converted to a fraction. Okay, next. Yes?
Could you do number 5 on page 95?
95, practice exam reader, page 95. We'll get there first. Number 5?
Yeah.
Okay, that's, just so people can see it, it's this question right here. Number 5 there. We're going from 3 to 2. Some people that year actually thought they should have memorized this, which I guess you could have, if you memorized it, you would have known the answer pretty easily. I was looking for a calculation. So, though you could have got it from memorization, I suppose. What you need to do is use the Rydberg equation. So, you would have said the change in energy equals Rydberg constant, 1 over n initial squared minus 1 over n final squared. N initial, it says in the question, is 3. N final, it says in the question, is 2. R sub h is a constant. And then you go hc over lambda. Okay? H and c are constants, and you can solve for lambda. What does that get you? When you get close to the end of the problem, either I would have to give you, if it was something in the middle, let's see what it ends up being. You can end up doing the calculation if you want, but it ends up being 5d, ends up being red. So you must have got a number, what, around 700 nanometers? Yeah. So get a number around there to say, oh, it's red.
And then 400 violet, correct?
Yeah. That's right. You should know the endpoints of the visible spectrum. You don't need to know the colors and hues. That's fine. Just the endpoint. Yes? Fall, do you know the page? Okay. Fall 2013. Give me a second here.
It starts on 86.
Okay. What number? So that's page 88. Is it the electron configuration problem? Okay, let's do that. Any particular part, or all of it, or? First one? Okay, cadmium 2+. Okay. Okay, cadmium 2+. The tricky part of this is it's one of the 2 exceptions of the transition metals. You need to know the 2 exceptions of the transition metals. And cadmium EC is in there. And let's just do this for neutral cadmium first so you can see how it'll work. So neutral cadmium, you go the previous noble gas. So that would be our krypton. Krypton, and then cadmium's in the second, so it'd be 5s2, 4d, all the way over, 10. Okay? So, I have to lose 2 electrons off that. Normally, you just take it off the last one that you just filled, so that'd be the 4d10. So you'd write 4d8 instead of 10. However, the exception you need to know is that transition metals will lose from the S before the D. So it's going to lose the 2S s electrons before the d electrons. So up here you're going to write krypton, not 5s2 4d8, but 4d10. Is that okay? Okay. So if you're fuzzy on those sort of exceptions, they are explained basically in the practice exam reader on page 75, getting a little bit into 76. What's the other exception? So this exception goes for all transition metals. The other exception is column of the transition metals, column 4 and 9, half fill the S before filling the D. So for example, chromium would not be 4s2 3d4, it would be 4s1 3d5. So that's for column 4 and 9 of the transition metals. Also explained on the same pages. There's some exceptions to that exception that you don't have to worry about. Okay, who's next? Oh, let's see how the time's going. Oh, we still have time. Or, I guess we're out of questions. Yes?
I don't have like a specific problem, but could you just do a problem that's like combining the gases and finding the pressure, the new pressure? If you combine two different gases.
You mean a Dalton's law? Mixing gases.
Yeah.
Okay. A typical Dalton's law problem goes as follows. That's right. Nobody really asked me Dalton's law this time. Usually, it kind of depends what it looks like. It doesn't always have to have this same setup, but typically you'd have a valve separating gas, say, A and gas B. Okay? And what we would do is say, okay, there are certain conditions before. Let's open the valve and find the final conditions, final partial pressures, etc. So what you would do is, it depends what they give you. So they either give you mass or, but let's say in our case, they'll give you, let's say the temperature for both is 25 degrees C. Let's say the pressure here is 1 atm. Let's say the pressure here is 2 atm. And let's say the volume here is 10 liters, and the volume here is 20 liters. Okay? So what you would say here, because it's related to ideal gas, you'd say, okay, moles of A, that's the first thing I need. That's PV over RT in the ideal gas law. So that'd be 2 times 10 divided by R, 0.08206, times T, which would be 25 or 298 Kelvin. Is that okay so far? So that'd be moles of A. Then you want moles of B as well. Same equation. So P is 1, V is 20, R is 0.08206, 206. And temperature, same temperature for both, which is pretty common. So you get a number for both of those, okay? Then what you'd want to do, so you can calculate that out, you would want to find the total moles, which is moles A plus mole B, okay? Then, if you want the total pressure, for example, you could find that right now at this point. You would just use the ideal gas law again. And there are different ways of doing this. This is just my standard way. Okay. Sometimes V total is given, but in this case, it would just be the sum of 20 and 10. But sometimes you put it into a third separate tank, so they'd have to give you that V total. But in this case, it's just 30. 10 liters plus 20 liters. Okay, N total is what we just found up above. It's moles of A plus moles of B. R is a constant, 0.08206. Keep forgetting the 0. And T is 298 Kelvin. So you can calculate P total pretty easily at this point. Now, not always, but often there'd be a step further where you'd be asked the partial pressures. In that case, it's straight up what we literally call Dalton's law. Partial pressure of A is going to be the moles of A, it's really the mole fraction, over moles total, times P total. Moles of A you found already. Right after that, you found moles total, and right after that, we found P total. So you have all these variables to plug into the partial pressure of A. No. let's go back. That's a great question. 2 ATM is before mixing. All these numbers are before mixing. Then you open the valve and allow them to mix. These pressures will change because the volume's changing. You've got another gas in there. So because things change, it's not necessarily going to be 2. In fact, it would be pretty unusual if it stayed at 2. Is that okay? Okay, cool. One last question. Yes, you're the winner. Okay.
Can we do an electron configuration for an element in the F block?
Okay. Hold up. Hold up. That has so many exceptions. Let me pick one that... you did that last time with Josh, right? Yeah. Okay. Here. Let's see, I think I have one. No, no. Now, where is that? Just want to pick one that doesn't totally mess things up. Here we go. Let's do, so we want to do electron configuration for something in the F block. Which one do we want to do? Let's do uranium. That's a nice one. That works out pretty nicely. Uranium. Now, I'm going to give you a periodic table on the exam that actually won't look exactly like these. Let me see if I have a sample for you that looks slightly more friendly for us. Here we go. No, that's not that one. That would be the answer. Here we go. We're going to use a periodic table that looks more like this. Okay? So, if you're going to do uranium, you're going to go to the previous noble gas. Okay? That's radon number 80. That's radon number 86 is the previous noble gas for 92. Okay? So, we'll write that down. Okay? Then, what is the next energy level? Anybody? 7s2. Okay, so let's write that down. 7s2. Okay? Then, what's this one? 6d1. Okay? 6d1. And then, notice now, after 89, we're going into the F block. So what's this level here? 5F, 1, 2, 3. There you go. Okay?
So we're given that periodic table versus the one in the reader on the test?
Oh, that's right. I forgot there's one in the reader. And the one in the reader, it's going to be one like this as opposed to one in the reader. The one in the reader is the same as the lab manuals. Okay, now just to point out something, because sometimes people get confused. Let's say we were doing element 104, okay? That would be, its systematic name, I guess, would be unnilquadium. So let's do that one. Unnilquadium. That would be UNQ. That's number 104. Okay? So, that would also be radium 7s2. Okay? Or radon 7s2. Okay? Then, notice what happens here. Now, all that information becomes irrelevant as far as lanthanum and actinum. So, you might say, okay, the next one is 3, 4, 5, 6, D1. But then what's going to happen to this F block? Totally fill. So it'll be 5F what? As you go through here. 14. So you might start writing, 6D1, 5F14. But then what you're going to notice, as soon as you get on the other side to 104, where is this electron going? Back into the D block. So instead of writing a 1, you're going to write a 2. Now it's filling the D block again. So there's a little interruption in the middle. It starts filling it again. Okay? Cool. Let's take a break right there.